Hello, niece and nephews. Today we're gonna learn about transport layer again in part 2 of chapter 3. In previous chapter, we talked about outline and we already talked about the objectives of this chapter. Today we're gonna talk about transport layer protocols. We can create a transport layer protocol by combining a set of services described in the previous section. To better understand the behavior of these protocols, we start with the simplest one and gradually add more complexity. Simple protocol. Our first protocol is a simple connectionless protocol with neither fault nor error control. We assume that the receiver can immediately handle any packet it receives. In other words, the receiver can never be overwhelmed with incoming packets. This is simple protocol. And this is FSMs for the simple protocol. Example T.T in figure T.19 shows an example of communication using this protocol. It is very simple. The sender sends packets one after another without even thinking about the receiver. This is a full diagram for example T.T. Our second protocol is a connection-oriented protocol called the stop and wait protocol, which uses both fault and error control. Both the sender and the receiver use a sliding window of size 1. The sender sends one packet at a time and waits for an acknowledgement before sending the next one. To detect collapsed packets, we need to add a checksum to each data packet. When a packet arrives at the receiver side, it is checked. Here is the topic of this chapter, part 2. This is figure of stop and wait protocol. And this is FSM for the stop and wait protocol. Example 3.4, figure 3.22 shows an example of the stop and wait protocol. Packet 0 is sent and acknowledged. Packet 1 is lost and resent after the timeout. The resent packet 1 is acknowledged and the timer stops. Packet 0 is sent and acknowledged, but the acknowledgement is lost. The sender has no idea if the packet or acknowledgement is lost, so after the timeout, it resends packet 0, which is acknowledged. This is for the diagram for example 3.4. Okay. Example 3.5. Assume that in a stop and wait system, the bandwidth of the line is 1 megabit per second and one bit takes 20 milliseconds to make a round trip. What is the bandwidth delay product? If the system data packets are 1000 bits in length, what is the utilization percentage of the link? The solution is the bandwidth delay product is 1 multiplied by 10 to the power 6 multiplied by 20 multiplied by 10 to the power of minus 3 equals 20,000 bits. The system can send 20,000 bits during the time it takes for the data to go from the sender to the receiver and the acknowledgement to come back. However, the system sends only 1000 bits. The link utilization is only 1000 divided by 20,000 or 5%. Example 3.6. What is the utilization percentage of the link? In example 3.5, we have a protocol that can send up to 15 packets before stopping and worrying about the acknowledgements. The solution is the bandwidth delay product is still 20,000 bits. The system can send up to 15 packets or 15,000 bits during a round trip. This means the utilization is 50,000 divided by 20,000 or 75%. Of course, if there are damaged packets, the utilization percentage is much less because packets have to be resent. To improve the efficiency of transmissions, multiple packets must be in the transition while the sender is waiting for acknowledgement. In this section, we discuss one protocol that can achieve this goal. In the next section, we discuss a second. The first is called Go Backend or GBN. This is a topic of Go Backend protocol. Yeah. Okay, let's go. This is a figure of Go Backend protocol. This is a picture of send window for Go Backend. Send window, the sequence numbers of the data packets that can be in the transit or can be sent. This is how sliding the send window works. The send window can slide one or more slots when an error-free ACK with acknow greater than or equal SF and less than SN arrives. This is receive window for Go Backend. And this is FSMs for the Go Backend protocol. Okay, let's go. And this is send window size for Go Backend. In the Go Backend protocol, the size of send window must be less than 2 to the power of m. The size of the receive window is always 1. Example 3.7. Figure 3.29 of the next picture shows an example of Go Backend. This is an example of a case where the forward channel is reliable, but the reverse is not. No data packets are lost, but some acknowledgements are delayed and one is lost. The example also shows how cumulative acknowledgements can help if acknowledgements are delayed or lost. This is flow diagram for example 3.7. Although acknowledgement 2 is lost, acknowledgement 3 is cumulative and serves at both acknowledgement 2 and acknowledgement 3. Example 3.8. Figure 3.30 shows what happens when a packet is lost. Packets 0, 1, 2, and 3 are sent. However, packet 1 is lost. The receiver receives packets 2 and 3, but they are discarded because they are received out of order. Packet 1 is expected when the receiver receives packets 2 and 3 is sent Act 1 to show that it expects to receive packet 1. However, these acknowledgements are not useful for the sender because the acknow is equal to SF, not greater than SF, so the sender discards them. When the timeout occurs, the sender resends packet 1, 2, and 3, which are acknowledged. This is flow diagram for example 3.8. The go backend protocol simplifies the process at the receiver. The receiver keeps track of only one variable, and there is no need to buffer out of other packets. They are simply discarded. Another protocol called the selective repeat or SR protocol has been devised, which, as the name implies, resends only selected packets, those that are actually lost. The outline of this protocol is shown in Figure 3.31. This is a topic that we will see next. Windows, timer, acknowledgements, FSMs, sender, receiver. This is outline of selective repeat. Timer is when a timer expires, only the corresponding packet is resent. Acknowledgements is the sequence number of the earlier free packet received. Send window for selective repeat protocol. And this is receive window for selective repeat protocol. Okay, let's go. And this is FSMs for SR protocol. Example 3.9. Assume a sender sends 6 packets. Packets 0, 1, 2, 3, 4, and 5. The sender receives an act with act number equal 3. What is the interpretation if the system is using go backend or selective repeat? The solution is if the system is using go backend, it means that packets 0, 1, and 2 have been received and collapsed, and the receiver is expecting packet 3. If the system is using selective repeat, it means that packet T has been received and collapsed. The act does not say anything about other packets. Example 3.10. This example is similar to example 3.8 in figure 3.30, in which packet 1 is lost. We show how selective repeat behaves. In this case, figure 3.35 shows the situation. At the sender, packet 0 is transmitted and acknowledged. Packet 1 is lost. Packets 2 and 3 arrive out of order and are acknowledged. When the timer times out packet 1, the only unacknowledged packet is resent and is acknowledged. The send window then slides. At the receiver side, we need to distinguish between the acceptance of a packet and its delivery to the application layer, and the second arrival packet 2 arrives and is stored and marked, but it cannot be delivered because packet 1 is missing. At the next arrival, packet 3 arrives and is marked and stored, but still none of the packets can be delivered. Only at the last arrival, when finally a copy of packet 1 arrives, can package 1, 2, and 3 be delivered to the application layer? There are two conditions for the delivery of packets to the application layer. First, a set of consecutive packets must have arrived. Second, the set starts from the beginning of the window. This is flow diagram for example 3.10, and this is selective repeat window size. The size of the sender and receiver window can be at most one half of 2 to the power of m. Example, m equals 2 and 2 to the power of m divided by 2, or 2 to the power of m minus 1 equals 2. The four protocols we discussed early in this section are all unidirectional. Data packets flow in only one direction and acknowledgements travel in the other direction. In real life, data packets are normally flowing in both directions, from client to server and from server to client. This means that acknowledgements also need to flow in both directions. A technique called piggybacking is used to improve the efficiency of the bidirectional protocols. Here is design of piggybacking in Go backend. Okay. A network is the interconnection of a set of devices capable of communication. In this definition, a device can be a host, such as a large computer, desktop, laptop, workstation, cellular phone, or security system. A device in this definition can also be a connecting device, such as a router, a switch, a modem that changes the form of data, and so on. This is position of transport layer protocol in the TCP/IP protocol suite. UDP is unreliable connectionless, simplicity and efficiency for error control. TCP is reliable, connection-oriented reliability. SCTP is Stream Control Transmission Protocol, reliable and transmission of user messages. Here is table 3.1 is some well-known ports used with UDP and TCP. Okay, let's go. Here is a summary of this part. We have discussed several common transport layer protocols in this chapter. The stop and wait protocol provides both flow and error control, but is inefficient. But go backend protocol is the more efficient version of the stop and wait protocol and takes advantage of pipelining. The selective repeat protocol, a modification of the go backend protocol, is better suited to handle packet loss. All of these protocols can be implemented bidirectionally using piggybacking. Okay, is the end. Bye bye.